we were born when it was released. Your age.
All right, so well, here let me preface stuff with this. So, one of my goals here in the master's program is to start getting our students publications. That comes for there's two reasons for that. One reason is, hey, it puts a little check mark on your resume, right? That because it's all stupid stuff. Most publications are you making a push in the research direction of things that don't work, right? So let's call it 99% of all research the result ends up being, oh, this is a bad idea, and we've proven it. It's that type of, but that's okay. I mean, that's part of what research is. You've heard me reference before in some of the other classes when we talk about design patterns. Design patterns are almost like built for academics, because all you have to do is come up with a funky name, pick a problem that is a, quote, common problem, and propose a solution to the problem. It doesn't even have to be a working solution. Just a solution that you think you can somehow propose that it might work. And then you prove that it's a bad solution. Paper. Okay? So one thing is it benefits you guys. The other thing is it benefits the department in terms of our accreditation. So we're working towards getting, I mentioned it to you beginning of the semester, about we're trying to get ABET accredited, which makes your degree mean more. So the more research publication crap that comes out of the department, the better. So we might as well, that's part of why we have the research course that a lot of you will be taking next semester, but we can spin that into some of our other classes as well, and create papers that just has a bunch of co-authors on it, that kind of crap. Make sense? So we'll talk more about that as we get towards the topic. So I want to spend our first part of tonight talking about is the idea of parallelism. What does that mean to you when we say parallelism, besides it being a difficult word to say? So we're going to minimize how often we say it. What does parallelism mean in terms of computing? Okay. So doing more than one thing at once. I think that's fair enough. Doing more than one thing I'm going to put in quotes here, once. Because once can mean a couple different things. Go ahead.
Executing instructions more than one at a time.
Okay. Executing more than one instruction at a time. Okay.
Actually, the CPU works in a process. In such a way, one process is taking an ideal time, the other gets executed. It's not exactly executing both at a time.
Yeah. So kind of what you're talking about there is we're going to split this into two things. There's something called SIMD, where you get actual hardware where two things happen. Well, actually, it's usually more than two things, where a bunch of things happen on a very small scale at the exact same time. And we'll talk about some examples of that. All right, but generally speaking, parallelism is when more than one thing happens at once. Under what circumstances is parallelism good? So let's think about pros and cons. So what's good about parallelism?
Faster. No wait.
Okay. Can be faster.
Well, yeah.
Yeah, not necessarily faster, but can be faster.
No waiting for an important instruction.
Okay. All right, so really what you're saying is no blocking. An instruction doesn't block. We can go and do something else while this guy continues on. Okay? Might help performance. What were you going to say?
There's a higher throughput.
Okay.
Like a 3-lane highway versus the county road.
Okay. So when you have your 3-lane highway, is that always better than a 1-lane highway?
It depends on the method, say so.
Okay.
A 3-lane highway compared to a 1-lane highway is always better.
Oh, so let's play devil's advocate. I like taking it away from technology. So give me some examples when a 3-lane highway is actually worse than a 1-lane highway.
People trying to merge, they'll cut someone off and
someone's texting and then smash into them.
In a 1 lane or a 3 lane?
3 lane.
Okay. But if it was a 1 lane, they would just like slam into them directly.
There's still an accident happening here.
There's only 2 cars involved, whereas like, if there's in the 3-lane highway, like everything.
What about all the cars behind the one car, you know, in the 1 lane, they're all piling up on top when the one accident?
Yeah. Usually it ends up in the ditch.
No, there's no usually here. You're making a scenario.
he's got a statistical model for it. It's like, look, once the Ebola thing was out,
We had to analyze traffic accidents.
I basically stood outside and just threw chunks of cinder block onto the interstate. You know, I just wanted to see what happened. You know, they usually ended up in the
No,
ditch.
like I was in Africa. I was in Africa this summer. Like
Our
that stuff
phone
actually
is dead.
like there's just blocks sitting in the road.
Okay, you're in.
Like, people like
I'm
sitting
trying
on
not
the
to
ground.
laugh, but okay. Okay, so you were
I've actually seen this.
okay, so you were in Africa. All right. So you saw what? You saw people ending up in the. Does Africa have ditches?
Yeah.
Africa's one big ditch. You can't say
So like the road is like terrible. Both wheels hardly fit on the road at the same time.
All right. So we got a dirt road,
Yeah.
That's not
Right.
even a road. We're comparing now a 3
and then what? Like a zebra runs out.
An elephant.
Okay, so an elephant trots out into the road. The guy behind the thing does some
No, the
clicks
car
and
doesn't
stuff.
have headlights, so he doesn't even see it.
We're driving at night now.
Yeah.
Okay.
So you're driving at high speed on a dirt road at night in Africa when you have elephants crossing the road.
You don't
What
know
is
they're
wrong
crossing
with
the
You
road.
don't know until you hit them or do
Yeah.
you swerve at the last minute.
You hit him. Either way, you end up in the ditch.
What?
What's it like?
Because naturally, the common way that way that you can ricochet off an elephant is that you can hit it and then move to the side. It's-
Does the elephant die? Does it just keep walking?
Yeah.
Just both.
What?
Yeah.
It dies and it keeps. I mean, now we got a Walking Dead episode.
Walking Dead, Africa.
You're pretty good. You're pretty good.
Well, I always thought that would be like the best thing for like the show like Survivor. You know, because now they're all like these tropical locations. You know, so everybody in the very first season of Survivor, which maybe was before you were born as well, as we've already covered that I might not have a real great idea when things actually
I
come
think
out.
it was like 90 days.
Yeah, I know people were like, you know, in suits and stuff like that because they took them from like a party, you know, a night before and dropped them into, you know, some island.
Sounds way better than what they have now.
But the point is that
2000, by the way.
oh, so the point is that now they all know they're going to some tropical place. They're all wearing bikinis and shorts and, you know, like ready to function. Instead of some guy getting dumped in the middle of the ocean, you know, swimming distance from shore in a tuxedo, like it was the first season. So what they need to do is they needed to mix it up a little bit. Just drop them in Antarctica.
They'll die.
Survive. I mean, it could be like
Kill the elephant.
it could be like a mini series.
Because they're already dead after 3 hours.
So it's filmed live. There's a bunch of people in bikinis
Basically what they
just
just
dumped
did.
onto something, just dumped on an ice shelf. And then the guys out there is all bundled. Survive. You just watch it happen.
We'll be back in 2 weeks.
It's gonna take 2 weeks.
Doesn't mean
Fully monitoring you.
Whoever's the strongest is gonna end up cutting into somebody and just living inside of them
you're
like a
gonna take
tauntaun.
advantage. If you're making that show, you're gonna take advantage of where you are. You're gonna drop them, take that Alaskan cruise for 2 weeks, and then come back and you just happen to pick them up.
You missed me saying somebody's living inside of one of them like a tauntaun. It's like, man, this class just took a turn. Do you know what a tauntaun is, old Alex? Tauntaun. Do you ever see? Have you seen the Star Wars movies?
Can we just watch Star Wars
No.
now? Because he needs to know.
So you know in the Star Wars movies, I think it's what was it, Empire Strikes Back?
Yeah.
So near the beginning of Empire Strikes Back, Luke is out like in the blizzard, and he almost dies. So he cuts open this animal called a tauntaun with his lightsaber, and he goes inside of it to keep himself alive. Actually, Solo gets Han Solo keeps it in there.
It's like a Lego. No, it's like
Have you seen
a
the
minifigure.
Family Guy one or whatever? He like cuts it open and he puts him in he's in the tauntaun. He's just like, oh, there's a Hotel 8 right there. Oh, really?
That's right across the street. Okay, back to our pros and cons of parallelism.
That one's before we were born.
It's going to be one of those nights. I just have a strong feeling about this. All right. So,
Okay.
so we've said parallelism.
Are we still in Africa?
Oh, that's right.
We're the 3-lane versus 1-lane.
Oh, yeah. 3-lane versus 1 lane.
I just need to find out, how did we get from a 3-lane highway versus a 1-lane highway to Africa?
Because
now?
he said he spent time in Africa with Ebola.
No, you said throwing cinder blocks out the window.
Oh, yeah. Chunks of cinder blocks just to see how many
Right,
people end up in the
but
ditch. And he said, no, we don't need to do cinder blocks. I saw this happen in real life with elephants in Africa. That's how we got to Africa.
You get weirder by the week.
I'm kind of liking him, actually.
He's getting more random than you are.
I mean, at first I was a little bit kind of iffy. He's like, but now, I mean, there's a level of instability there. You almost feel like the whole sandwich artist thing is just starting to get to him.
Yeah, I actually turned in my 2 week.
Did you?
Really?
Oh, wow. See, it is getting to him.
It is.
So are we going post office next?
Mathnasium.
What's that?
What?
Gesundheit.
No.
Yes.
You heard what he said.
Mathnasium?
No,
Yes.
it's actually a meth lab.
Mathnasium.
Oh, it does start with meth. The word meth.
Meth lab.
Mathnasium.
That's what they call it now to make you think it's not one, but it is.
Okay. All right. So tell me about it. So it's called.
It's a private math tutoring company.
So is it mathnasium or methnasium?
Mathnasium.
Oh, it is math.
Oh.
But meth sounds funnier.
Yeah.
Okay.
So he's a meth dealer.
So private tutoring lab. I get it.
They have a couple kids who come in and learn math, but the rest of the time,
The rest of the time, we pretty much just do a 24/7 cook. Isn't that what
what's
they?
behind that door? Yeah, nothing. You don't go near that.
you don't want to go near that. All right. So we were talking about 3-lane highway versus 1-lane highway. Give me a scenario when a 3-lane highway is actually worse than a 1-lane highway. And I want to start thinking about this in terms of hardware to some extent. So I'm not really looking for things like texting and stuff like that. Go ahead.
Well, if you don't have the traffic to need 3 lanes, the fact that you have to maintain the 3-lane highway is all the maintenance, construction, and everything else that the money goes into it. And takes a
So
lot.
maintaining 3 lanes is more expensive than maintaining 1 lane.
Installing as well and setting everything up.
There's time to install, takes up more space, that's things you can't use for other stuff. There's overhead.
Yeah.
So if we're taking this back to our, there's overhead involving 3 lanes.
That makes
Now-
more jobs because we're making America great.
Making America great.
One racist statement at a time.
It's true. Okay, so when do we decide? So if we're looking at building highways, when do we decide to put in a 3-lane versus a 1-lane? What becomes that decision point when we say, okay, it's worth it. It's worth taking up the extra space. It's worth spending the extra money. It's worth having the extra long-term commitment of overhead.
There's enough traffic that nobody else can turn on because
Who
there's
scheduled
always-
those 3 again?
What happened?
Oh, we have class next semester from 3 to 6, 6 to 10 on Monday.
Which is my class?
6 to 10.
Oh, well, we'll just move it to a different day.
Can we not have the class at 3s again?
That's
Blackler.
yeah, it's not my department.
Oh my gosh, I'm gonna stab.
Don't worry about my class because I'll.
Figure it out.
That's fine, but I keep having to leave work.
Yeah, well, that's not my problem. But if I can do something to keep my 4-day weekends, I will.
Has been for this department for working professionals for an advanced degree, and the working professional has to leave work in order to do it.
In all honesty, I think that's an extremely valid point, and I think you should bring it up.
I have been the whole semester.
Maybe bring it up again. I do think it's a valid point. You know, I don't want to be here from 6 to 10 p.m., but that's what we're trying to do is be able to get working professionals in so they work on master's degrees. So I get it. It's not ideal for the faculty members, But hey, we want to have enough people in the classes. This is what you got to do. So I agree with you, which is pretty rare, actually.
You agree with me more often than not.
Yeah. But I can understand the dynamic because, I know the faculty members personally and they're my friends, so I understand they have family obligations and stuff like that. So somewhere in there, where's the balance, right?
I mean, when you only have 3 faculty members who are eligible to teach these
Yeah.
classes.
No, I get it. So it's
the ones that aren't eligible and just have a shit show.
All right. So we've discussed that there's some overhead with the 3-lane thing. Now, if we have a lot of traffic, so for instance, Milwaukee, if during the week you're trying to drive down from Mequon or something like that down into downtown Milwaukee, when do you avoid that interstate?
Morning.
No.
7 to 8:30 a.m., something like that.
Yeah.
Yeah, that's probably it. That's your death zone. No, I mean Milwaukee traffic isn't anywhere like a Chicago traffic, but relatively speaking, you're going to have a slowdown, right? Okay. Chicago, you just avoid. Period.
No.
I drive through Chicago quite often when I go down to Illinois to visit my folks, but you pretty much don't. You want to hit Chicago around. You want to hit Chicago around 9:30 a.m. on your way down. You want to miss the probably 11 to 1.
Yeah, 1
And you want to miss the 3:30 to
7.
3:30 on
On.
until the next morning. You just skip that. So when do we actually make the decision that 3 lanes make sense? When are we willing to give up the extra real estate or willing to give up the extra money? We're doing it because it's faster, right?
When we can't make the user think that we're fast anymore.
Okay, gotcha. I think that's a reasonable answer. So when the user is no longer tricked, when this is no longer isn't when we look at the interstate as a synonym for freeway, fast, whatever, and it's no longer that, and taking back country roads with elephants and zebras makes more sense, then you add some more lanes. Fair enough. All right, so the benefit of our 3-lane road is it's faster, right? It's going to be faster, even if it's underutilized. Will it still be faster? If we don't quite have the growth, if we don't quite have the population right now to work with it, it's still going to be faster than the 2-lane road or the 1-lane road, right? Or as fast, I suppose. Now, does that mean we plan for the future? Where's that decision made? Do we just decide, well, let's just, we're building it for the first time now. Maybe we make it 3 lanes now.
Load balancing,
Okay. Tell me how load balancing plays into this.
like expecting future traffic so that making a proper decision to divide the single lane into 3.
Okay, so then why not make it 12 lanes?
It's going to be a lot of cost expensive. It's not a manual approach or optimal approach to process.
Okay.
It's not about 3 or 4. It's more than 1.
So one advantage we have in computer hardware is it recycles, let's say, like yearly. Could be more significant. Usually it's more than once a year, but at the very least, when we think about processors, which is kind of where we're going with this, we look at a new processor, a new major processor coming out every year. So when we make a decision right now, that decision kind of locks us into the next year. Maybe good, maybe bad. It needs to be accurate. We can't make a decision that's literally that makes the processor dysfunctional. But most of the time, we ride out a decision for a year. We look back and say, okay, we're going to keep the stuff that worked. We're going to fix the stuff that didn't, that could be made better, right? So it's we have the flexibility, even though it's hardware, to make changes. We're not having to dig up interstates, all right? So with hardware, it's not like us trying to build a new road in West Bend and just decide, well, we'll just make it 12 lanes, right? I'm sure they'll grow into it. But it actually is interesting to draw the parallel with, pun intended, I guess, with real life roads. I mean, where he lives down in, so you're actually from down there, right, in Florida?
No,
Oh, but you've been down there for how long?
a couple of years.
Okay, so down there's really high population density. So he's like in the Fort Lauderdale area. Because a lot of people have gone down there to retire. So you go down these roads. So like the equivalent of Portland, Washington Road down there might be a 4-lane road, and it's not enough. There's so much congestion. There's such high population density. Who would have thought they would have needed something more than 4 lanes? Well, they do.
There's a lot of people, plus it's all old people driving.
The old people aren't as bad of drivers as you think they are. New Yorkers stay aggressive until they die.
That just sounds hilarious.
I mean, my grandpa, well, he was from Philly, but he was a Philadelphia Jew and living down there, and he kept driving like to a McDonald's that was about 2 blocks from their house, way after he was defined legally blind. I'm not kidding. I mean, you had to help this guy into restaurants and stuff, and he was driving a car.
How did he die again?
They're just old. Yeah, no, that guy was old. Yeah, he was like I guess the epitome of, like you should do some sort of statistical model of that. I mean, every time I was with him, he would eat salami. Anyway,
he was the epitome of Jew.
Yeah, I mean, it was fine.
Maybe that kosher.
But he wasn't like super. He didn't eat like a health nut or anything. He was a heavier guy. Just ended up getting too old. Everything wore out. That's the way to go, right? But yeah, so he was driving while he was blind. Never had a problem.
Maybe
That you know of. That got reported. I'm sure he hit a few things in his day.
I could actually see him like hitting dumpsters and stuff. Because that dude couldn't. I mean, I don't even
Maybe
understand.
it was one of those things like, who is that like old cartoon or whatever where it's the old guy who can't see Mr. Magoo or whatever it is?
Yeah.
Is it like that where everybody else is just crashing because he's driving like a maniac?
And he'd been going blind for a while too, because I remember as a kid, when he was driving, when you want to change lanes, you put your turn signal on, you check your mirror or you check your blind spot, right? That's not how Grandpa changed lanes. Grandpa changed lanes by swerving in and out of that lane and listening for a honk, because his hearing was better than his vision.
I mean, if it worked. So he was Mr. Magoo.
pretty much.
The Jewish Mr. Magoo.
Yeah, it's true.
So Mr. Magoo Mr. Magoostein.
All right, so parallelism can help us go fast at the cost of overhead and electricity, battery power, all this other stuff that we might be dealing with our mobile devices and that kind of crap. Okay, so is parallelism always the right solution?
If you're AMD, it is.
That's true. Now, certainly, and I want to have the discussion in here. Well, at least the initial discussion. I don't want to think about battery power. So let's not think about like the power it takes to run this thing. But we want to still think about the benefits and costs of parallelism. So again, let's keep this in a real life scenario. If you have a task that you need to accomplish in real life, do all tasks benefit from having more than one person working on them? The old proverbial, how many people does it take to change a light bulb?
It's a group project.
Well, I mean, so the punchline is there are certainly things. I mean, the example I always use when we talk about multiple processors is, if you're picking up garbage in a park, let's say. So let's say I can pick up garbage at speed 10. And let's say the 3 of you could pick up garbage at speed 9. Slightly slower than
Are
me.
you faster than us?
It's efficiency. Okay, it's all based on bulk. It's fuel. Okay, you guys are. Okay, I mean, when you're picking up the park, you're not eating. I can keep trucking when you run out of energy.
How does he keep going?
The guy's got 350 pounds of stored fat. I'm pretty sure as long as you keep watering him, he's good for a while.
Just keep going. I've been storing up for this for a long time.
That's not going to work out well in a zombie apocalypse.
Unless
Because you don't need to be that fat to get away from them because they're slow. They're zombies.
Didn't we calculate that in the first class, like how long you could survive?
Usain Bolt, wasn't it?
What?
I thought that what we calculated was
Yeah.
how big of a head start I would need on Usain Bolt to win,
Yeah.
in an Olympic running event.
a step till the finish
Right. That's accurate.
line. All right, and right foot and lead one.
Go. All right, so the three of you are are able to pick up trash in the park at speed 9. I'm able to pick up trash in the park at speed 10. Slightly faster. Now, do we all feel pretty confident without having to go into the math of this that the three of them are going to clean the park up quicker than I will? Provided the park is of any sort of reasonable size, not like we're all fighting over one piece of trash. Right?
Well, that's a fair argument.
Well, but the point is that generally speaking, that is a task where division of labor is helpful. Right? Changing a light bulb, if I can change the light bulb at speed 10, and each of these guys can change a light bulb at speed 9, and we have one light bulb to change, who's going to win that race? I will. Even though there's three of them and one of me. Because it's a job that doesn't benefit for having multiple people working on it.
You're going to be on a ladder, so we're going to make some space.
So I fell on a coffee table yesterday.
How exactly did that happen?
I was in my computer chair,
Yeah.
and the left arm ripped off of it,
You just supposed to.
and then I just fell on my coffee table.
The arm came off.
Yeah, so I was like repositioning myself, like to scoot back in the
okay.
chair, and then the arm just ripped off, and then I went boom.
It just went down.
Yeah,
Did the coffee table survive?
yeah, it did. No problem at all. It was from IKEA. This is just strong stuff.
Well, typically people get upset and just start beating it when they try to put it together. So
Oh, really? I thought that was the whole thing. IKEA stuff is easy to put together.
No,
That's not that true?
IKEA is known to be like the thing that you can't because the instructions are too crazy.
Oh, really? I didn't know that.
Sweden themselves make fun of themselves because we made these things that no one could put together.
Oh, is that the thing?
Yeah.
Oh, see, I mean, I've never actually.
the joke is
I have
before you
people.
get married, you have to
I have people that.
you gotta have the bride or the groom put together a piece of furniture. If they don't walk away from each other, how they can get married?
That's a good thing.
That's
to
probably
do.
a pretty decent research paper you can write on that one. That's probably there's some mathematical soundness there that
You could probably also find some religious stuff in there, get the point in there. Christian worldview.
Christian worldview. Nailed it.
Marriage and IKEA. How can they benefit?
I didn't realize IKEA was supposed to be difficult to put together. I thought that was.
That's the idea. It's
I thought it was like highly engineered. I thought it was like.
It's
It's
super engineered,
yeah.
but it's like people
It's
have
not gonna-
issues finding the instructions in English or something
Oh,
like that.
I got you.
It's supposed to be possible.
All right, so we could say that parallelism is sometimes beneficial. Fair enough? Not always. It's not always the right tool, but it is something that we should always consider. Now, what flavors does parallelism come in?
Strawberry.
All of it.
So when we think about doing things in parallel, we had a couple of definitions we threw out here. Is there only one kind of parallelism as it relates to, even in real life, but relates to computers? What are some examples of parallelism, I guess, in real life?
In real life.
Sure. Oh, you want to give me computer ones?
Yeah.
That's fine. Let's go with that.
You got
Give me some
cores,
examples.
You got threads. You got
Okay, well let's deal with each one. So you said so multiple cores. Okay, so multiple cores, that's a form of parallelism. How does that work?
you essentially have. You can run separate programs on separate cores if you need to, or you can split one program up from multiple cores.
Okay, now what's a core?
The actual instruction set that you were running.
Okay, so it's a general purpose CPU.
Yeah.
Right. So a core is a powerful thing. It's not a simpleton little thing. It's a general purpose CPU. We have two general purpose CPUs sitting next to each other, or four of them, whatever. But we have general purpose CPUs, and those guys are each given tasks. And as long as those tasks can happen without impacting each other, they get the full use of that CPU. Okay, fair enough. What other kind of parallelism?
Threads.
Threads. Okay, tell me about threads.
It's essentially the software version of cores. I guess is the most simplest, stupid way I can describe it.
Okay. Okay.
I don't.
Threads. Threads are software. Okay, you already said threads are software based. There is no guarantee that threads increase performance.
No.
Threads are scheduled secondarily to by the operating system, not the processor itself. So there's no guarantee. You might have things that you believe are happening in parallel. That is, they're happening in a non-blocking way. But they're actually being scheduled on the exact same CPU, so they're not happening at the same time. So the thread version of us picking up the park would be the three of you are each a thread that know how to pick up trash in the park. Okay? Yet there's only one core. We're in a single core processor. So even though the three of you are working independent of each other, only one of you is actually picking up trash at any single point in time. Does that make sense? Because there's only one core so only one thing is happening at a point in time, even though none of you are blocking each other.
Like Josh would be trash.
All right, so why? Because he's closer to the ground.
I didn't think of that. That's a good reason.
Wow. Going there.
Nah, I feel like Dave and I probably just go ahead.
Actually, I had this discussion last week, though. I mean, is he closer to the ground? How tall are you?
6'2".
Okay, how tall are you?
Like 6'1".
Okay, yeah. So you're like 5'10", right? Yeah. I thought he was like 5'3" or something.
It's from the wrestling. Like when you have so much pressure just pushing you down, it keeps your spine.
Well, I mean, I don't know. I'm pretty tall, and I have a lot of pressure pushing me down.
It's pulling you down.
There's gravitational complexity going on up here.
Didn't you lose a decent amount of like height when your
Yeah,
spine
I've
collapsed?
lost over almost 2 inches.
Wow.
I used to be like a true giant.
Imagine
Well,
if you
that
had
was
the weight
before
then.
you were super fat.
What if I did what?
Imagine if you had the weight then. You're like 6'4", 6'5", or whatever.
Yeah, I was about 6'5", right?
With all the weight, oh man, you would have been
Andre the Giant.
Oh, it's. I mean, I'd be thin if I was like 13 or 14 feet tall, like one of those elephants. Actually, they're not 13 or 14. What's an elephant? Maybe 10 feet tall?
I don't know. He's the one who runs into him
Yeah.
on a regular basis, apparently.
African elephants are the biggest mammals.
Okay, how tall are they?
I'm not sure.
He sounded really scientific for a
11
split
feet.
second. Then he didn't follow through.
the
Someone
African
threatened
bush
to charge
elephant
him
can
for
get to 11 feet.
11 feet? Yeah, so if I was the height of an elephant, I'd be in pretty good shape.
It's got a length of 21 feet.
Really? That's a big butt.
Somebody did like, he's like a 7'8" guy, he's like the tallest guy in America, did like an AMA or something on Subreddit Tall. So then he's this like 6'8" guy who's like, what's it feel like? And he's just like, I don't know, I'm just taller than you, shorty. He's like, I'm 6'8" and I just called short. Like, what? He's like,
Oh, the
6'2".
guy was 6'8". He just got called short.
It's like, and all these like 6'2".
I always find it entertaining when I'm walking in the halls or something like that. There's somebody who's taller than me, because most of the time I'm the tallest person in the room, or right up there. I always consider myself to be kind of on the highest end of normal tall.
Yeah,
Any
it's
taller, you're on the
Yeah.
You're on the
Yeah.
freakish side.
yeah, right. Okay, so threads, not true parallelism. Threads are faked parallelism, right? Threads are faked parallelism. That might
Yes.
become
Yes.
true parallelism in a multi-core situation. Fair enough? Okay, what other examples of parallelism do we have?
distributed computing.
Okay, tell me about that.
I guess the most generalistic example would be you have a queue up somewhere, and then you have a bunch of computers pulling from that queue, and they each can process that on their own time, so they can pull from the queue and process the event and do whatever they need with it.
Okay, so the idea would be that, well, here, we'll keep it with our election scenario. So we have a whole bunch of people that we're supposed to be making phone calls to tell them to vote for candidate X, Y, Z. So we have a list we're all working off of, a shared list. And we're making phone calls, but the idea is that none of us should call the same person at the same time, right? Or the same person twice. So we want to each be working off the same list, but calling unique people. So there's overhead with that. The overhead is what? Managing who's next on the list, right? Because if me and Smart Tim go and grab the
At least it's not unstable, Tim.
well, this is Smart Tim and Unstable Tim. He's not unstable yet. He hasn't snapped.
No, he's
but
already there.
once he's at the meth place, then maybe we'll see.
How do you think he got hired?
Okay, so we both grab this list at the same time. We both get the same number at the same time. So now we have to have overhead to protect this resource. That's just like our 3-lane highway takes more stuff to maintain it and that kind of crap. All right, but the idea is that if each of us are working independently, we're each our own computer. We're a distributed machine. We have our own brain, our own ability to do stuff. We get a name, we make the phone call, and we're working autonomously relative to each other, but we all have a common goal. Okay, that's distributed computing. Okay, great. Okay, what else? Any other examples? Let's stick with this this idea of our distributed computing here. Now, if we had a massively multi-processor machine, you know, our machines today are what, like quad core, or there's a 6-core for desktop processor. You get dual 6 cores, so you technically have 12 cores, whatever. So you get a machine that has lots of independent cores in it. In that example, if we have enough stuff and we have the oversight for that list to distribute it, we could have one machine act like this distributed computing model we just talked about, right?
Yeah.
There's no reason why, because basically each machine is a processor. You know, today's model, each machine's at least a dual core processor, maybe even a quad core processor, but you know, each machine is at least a single core processor, and they can each do their own thing. If we have a single machine with lots of cores in it, that guy could be his own relatively small scale distributed environment. Is that always better? So kind of a good example with that when we talk about hardware is, so I'm going to give you a $10,000 Mac Pro with 32 gigs of RAM and 12 processors of the Intel's highest end Core i7 Xeon, blah blah blah. You go to the Apple Store, you just max the machine. Just see how big you can get the number, right? Most of us have done that at some point, right? Like, how expensive can I make this? Right? So, you get that, or you get a $3,000 laptop.
So basically, one max.
That's fine. Which do you want?
3 of them.
Well, one or the other. You get to choose one or the other.
Do I get the 10,000 or the 3,000? That's it. Like I don't get 3 of the 3,000.
No. You get the $10,000 one, or you get the $3,000 one, plus $1,000. Sweeten the deal a little bit. And you're not allowed to sell either one. Because I saw that's where you're going. Well, I can sell the $10,000 one for $7,500. Go and buy the $3,000 one.
Okay, let me ask this: what's in the $10,000 one?
He just said so.
A bunch of cores, a bunch of RAM, super high end desktop computer versus super high end laptop computer, but less high end. Less cores, less RAM, because it's a laptop rather than a machine that's meant to be multiple, like heavily multi-processing.
Laptop.
So you want the $3,000 laptop plus $1,000 bucks,
Yeah.
as opposed to the $10,000 machine?
Yeah.
Why isn't the $10,000 machine better?
Because I have my desktop at home.
Well,
I can use a
okay.
laptop.
Is your desktop at home going to be anything like the? You have a laptop right there in front of you.
Yeah, I have 2 laptops.
So what?
So what's your argument for the laptop?
I can use that more than I could the desktop.
Okay. Give me a performance reason why you might pick the laptop over the. Because you're doing it more of an economics reason.
Power.
Like, well, yeah, I kind
Better
of.
than this one.
Power.
Okay. Tell me about what do you mean by power? You're just saying a word.
No, it's you're gonna save a lot of money on using energy if you get the laptop versus the desktop.
Not necessarily.
All
You
right.
get a decent enough power supply.
I get it.
You're still gonna pull a lot more wattage.
Yeah, but I mean, won't that $10,000 desktop do so much more?
Depends what you're
Buy
doing
a
on it.
$100 crappy laptop and a
All right, so let's here. You guys are too close to this problem, I think. Let's reboot the example. All right, you just moved into a house.
I can't afford a house.
Okay, you just did. Somebody gave you a house. Okay. Free house.
You want to give me a house?
Happy inheritance.
You have free house. All right, so now you have to. Somebody's going to give you a lawnmower. So you either get a normal push lawnmower or one of the big old honking riding lawnmowers. Like, I mean, we're talking about like the tractor type. You know, that just can mow a pretty big yard pretty quickly. What you going to take?
Depends on how big my yard is.
I just said it's a pretty small yard. The tractor will fit in your yard.
Just take the tractor, Tim.
What's the right tool for the job? Okay, push one. The push one's the right tool for the job. Okay, now where are you going to keep that tractor? Let's say you took the tractor. Are you going to be able to mow the yard quicker with the tractor? Yeah, possibly. You probably do it in a couple of sweeps.
Heck, you can go mow the other neighbor's lawn. What time it takes you.
That's exactly what you do. You mow
You
the other
use
neighbor's
their
lawn
yard
in
to turn
exchange
around.
for storage on their lawn of your tractor.
Just find the guy with the biggest garage. You go mow his yard. Store your lawnmower there. All right, so that big tractor lawnmower is kind of overkill for most applications, right? But every now and then, when you got to go and mow a football field, every now and then,
Do you have to mow a football field every now and then?
sure.
Do not.
No, I hire people.
I live in the
All right, so every now and then when you have to do something, a big job, then having that lawnmower is going to come in handy. But a majority of the time, you get no benefit from it. You know, the time it takes to get the big lawnmower from your neighbor and bring it over to your house and do a couple of swipes and then go and park it back there, you might as well have spent the 10 minutes just to do the push lawnmower across your yard, 8, 9, 10 times and be done. Right?
bragging rights. Why is your lawnmower bigger than your car?
Why does it have a lift kit? Who needs a lift kit? I mean, you kind of want the you want the blade close to the grass, don't you? So yeah, that's why I did have a lowering unit on that. So you lifted the whole vehicle up just to lower the blade? Yeah.
Yep.
That's what I did.
What do you mean you lowered your lawnmower?
I raised my lawn. The entirety of my lawn is elevated 7.5 feet to make it compatible with my lawnmower.
It also doubles as a wall. No one's robbing my
paid
house.
for it.
All right, so punchline is a more expensive, more, quote, powerful computer doesn't necessarily equal a better computer. Depends what kind of job you're using this for, right? So in real life, what are some tasks that you might use that $10,000 computer for where it would be worthwhile to have that machine? Forget about the dollar sign associated with it. When would it be the right tool for the job compared to that nice laptop? And I'm thinking the answer is something from Parallelism.
Training a neural net.
Who? Training a neural network. Okay.
You're gonna mow a lawn.
No, you got to. See, I feel like you just threw that out there. You got to defend that. Training a neural network can be.
It's there's tons of computations that go into it. It's best done by a GPU.
But can they be done in parallel?
Yeah.
Tell me more about that.
Well, it's matrix operations, which is
Oh, okay. So you can't have you're not testing two different inputs at the same time.
No.
You're increasing the speed of one input test by doing the math in parallel.
Yeah.
Fair enough. Okay. So I guess for really, really complex neural networks with very complex data inputs, sure, fair enough example. But it would be very difficult to train a neural network. Actually, I mean, it's actually a pretty good example of something that would be potentially impossible unless you came up with a special purpose neural network to train a neural network in parallel, because each time you're updating the weights between the neurons in the network. You can't have 9 different threads all updating these weights.
The best I can see is that you would have to have like some sort of database, atomic database, that when someone else is, even then.
Well, no, I don't think that could work either, because when you're
Oh,
determining
yeah.
whether or not the neural network got the right answer, you're doing that based on the old
Right,
weights of.
yeah, but you would.
So,
Well,
but I
test
mean, you have a
multiple
decent
images
point
at
with
one
the
time,
math stuff.
and then update, test all the images again. Update, test all the images again. Like you can run multiple things through at the same time.
Right, but
But
you.
then you update the
but
numbers
you-
once, and then you run them through again.
Okay, so you're saying maybe come up with an algorithm where you're updating the weights between nodes based on several outputs rather than each individual output. So instead of being very granular and saying, okay, here's an input, is it right? No. Fix it. Here's the next input. Is it right? Yes. Don't change anything, so on and so forth. Maybe you feed 10 through, and if it was 80% accurate, you don't change anything, otherwise you do. I guess you could do something with that, but okay. We're going to call that the math side of that's probably a decent example. Okay, give me another example of, maybe a practical example of when that $10,000 computer is going to come in handy.
Video games.
Okay, tell me about that. I don't know if that's necessarily true. So what about video games do you suspect a massively parallel machine, or I use the word massively loosely, how might that help?
I can play Overwatch, League of Legends, and anything else I want at the same time.
At the same time. It's like, now I have a reason why my skill in it sucks. I can just tell people I play.
Prove that game. Well, it was my turn.
Unless you're botting 15 instances of WoW on the same computer.
I play all my first-person shooters with the monitor off. No wonder you're so bad.
Some of my first-person shooters using a makeshift controller out of twine, forks.
A squirrel that I have held hostage. All right, so keep going. Give me a practical example of when that $10,000 computer is going to shine.
When you're doing a racing simulation where you need like 3 4K monitors like wrapped around you, and
It's still graphic.
Yeah, even then, it's probably just multiple GPUs. You can get a way less than a $10,000 computer and probably drive that with good GPUs rather than having a $10,000 computer with one good GPU. So I don't know, driving monitors, is that beneficial?
Build box.
Tell me about that.
Like you got a team of developers or something, and they want to push things to a central building server that will compile your entire source code. And if you have them multiple doing it at the same time, it's a very high CPU intensive process. And if you have multiple builds going at the same time.
Okay. So kind of an example of distributed computing where they're each working independently as developers, but then they submit their code to a central server that keeps the current version of the checked-in code built.
Right.
Okay, fair enough. Give me something practical.
Video rendering.
Video rendering, I think, is a very practical example.
Data processing in airline trafficking.
I guess data processing is that's the correct answer. It really depends on how many people are using the server. I'm thinking from an individual perspective. If you're just one person using a computer, when does it come into play?
So video rendering was or wasn't?
I think video rendering is a good example. So most of us in here have had a scenario where we've had to convert a video that you probably got illegally, right? To put it on iTunes or something like that. If you took that same, this goes right back to like the cleaning up the park example. A machine that can do many, many things at once within itself is going to be able to convert video much, much, much faster than a machine that can only do 1 or 2 things at once. So your laptop could convert an hour-and-a-half movie in probably an hour and a half. That $10,000 machine can convert an hour-and-a-half movie in probably 4 minutes. Yet your laptop versus that $10,000 machine in terms of checking email are going to be the same. Makes sense? You're not doing a really complex thing. Punchline is parallelism isn't always better. Okay? It's what's the right tool for the job. Now,
I knew about it because when I made the video of you screaming with Taylor Swift,
see, I needed to take it up a notch.
I had to do the double pass. I think it was great. I still have it. Still on
Is that
YouTube.
spelled right?
Yeah.
3 R's?
Yep. 7.
5. Surrounded by parentheses.
What's concurrency?
Hard.
So what does concurrency mean as it relates to parallelism? When I say two things are happening concurrently, what does that mean? They're happening at the same time, right? Okay? So we've been, so far today, have we been talking about concurrency? Okay, so really, we've been using parallelism and concurrency synonymously. All right? Is there another form? So actually, let's expedite it a little bit. So he's been talking about some math operations, right?
I was gonna bring that up as an example. To run simulations for Ebola, it takes like 12 hours on here
Okay. Why?
because I'm simulating 3,000 different outbreaks and solving the problem at each outbreak 5, I think 7 different ways.
Okay. So what kind of math is it doing that's caused that is so resource intensive?
I think much of it is coming up with random numbers.
Okay.
Floating point
Creating-
calculations.
Like creating a random outbreak is, I've been told that coming up with random numbers is very computationally expensive.
And potentially inaccurate. There's all sorts of research dealing with good sources of randomness.
Well, I think that's been pretty much solved now.
I don't know. What's random? Now we're going to get into the Christian worldview stuff.
Random as far as naturally random. Naturally random. Random events occurring naturally. You can't mathematically generate natural random events. So I think what most people do for true random is they'll have a sensor, I think like wind sensors or something are one of the most current, and they'll use the wind sensor to figure out, generate a random algorithm from the data that the wind sensor produces.
Okay. But even then, I mean,
I don't think it's exactly a wind sensor. I forget, but
I got you. So you're saying that they somebody has a mechanism for getting randomness is pretty well. All right, fair enough. I don't want to get too far off on a randomness tangent. So if we've been talking about concurrency up to this point, what is another kind of parallelism? We've been talking about things kind of in terms of general purpose parallelism. You know, earlier I kind of pointed out this idea when you were talking about multiple cores, that these are two general purpose cores. Fully powerful, can do all the magic tricks that instruction set can do, but two separate ones. So we can feed each of those guys, it's, something to do, and they can do it in its entirety because they have the full talent of that instruction set. Are there problems that we can break down into tiny pieces where we can have parallelism occurring in simple machines that actually benefit? Let's think about this in terms of a TV screen or a computer screen, doesn't really matter which of them you're thinking about. Let's say that we have a picture up on the screen. So this picture right here. It's a picture, I guess. Let's say we want that to become dimmer, so less bright. How does that happen? I mean, obviously, I push the button on here and see it dim. Okay, right. So here we'll mimic it. Does it actually get dimmer on there?
No.
See, nothing. Okay, it got dimmer on a laptop. Trust me, it did. So I push the button. What's actually happening under the hood?
It's controlling the monitor brightness of the displays.
Okay, so there's a whole bunch of pixels on this screen, right? What information are we keeping track of for every single pixel? Our brightness is probably one of them, right? How much light does this one pixel have? Should show up on this one pixel? Then probably its color. So RGB, some
Except for that one people that decides to die.
That's right. So 8-bit values for red, green, blue, and then whether or not the thing, at what level is the thing bright? Maybe, depending on the technology you're using, there's a big range of available brightness. Okay, so if I want to make my screen darker, if we use a non-parallel approach, what would I do? Turn the whole. So we can synchronously go through our monitor here. Think of our pixels as just a giant array of pixels. So, whatever I think this is a 2K screen. I think that's the thing. So it's like 25 something by whatever. So, let's say there's 3 million pixels. Just to use that as an example. So I got to go through each of 3 million pixels in order. Tell each pixel to reduce its brightness by 15%. Let's just say is what I'm doing. What's that going to look like to the end user? So I'm going to see like the kind of lights going off like at the sweep, right? Actually, might be kind of a cool effect. What's up?
Like dominoes.
Yeah, I guess that is true.
Back in the old days of the screen updating.
Yeah. So now screens go pretty quickly, so we might not notice, right? Depending on how many pixels we're dealing with here. Maybe 3 million pixels you might notice, but all that's happening really, really, really fast, so it's possible we wouldn't notice. But how can we do it better so we make sure we don't notice? Does it really make a whole lot of sense to go through 3 million individual pixels, tell each pixel to make themselves a little bit less bright? Let's take this down to a real life example. So now we're back to our voting. All right, so we got a state that we got to mobilize the vote and get everybody out to the polls. So I'm going to take one sector of the state. You're going to take one sector. We're each going to take a sector of the state. Okay, we want to turn down the lights, if you will. We want to dim the pixels in that sector. All right, so we each go out, and now we're in charge of that individual sector. So instead of us dealing with a pixel on a per pixel basis, we're instead dealing with a group of pixels, group of potential voters. So maybe I'm in charge of 500 voters, he's in charge of 500 voters, so on and so forth. But is he able to handle 500 voters all at the same time? Could we solve his problem concurrently?
It would be making a junction point for all the pixels based on the value at the junction. They all respond at a time.
All right, so if your goal is to get these people to get out and vote, that's our goal. Do you really need to be a fully functional person in order to do that? Or you go there and grab them and drag them to the polls? It's a very specific problem that you're solving, right? We were stretching it a little bit, but generally speaking, if you want to get 500 people to the polls, you only need somebody who can grab onto somebody and take them to the poll. They don't need to talk. They don't need to convince them. They don't need to do any of this other stuff, right? There isn't a whole lot of logic. It's a simple machine. It's not a full-fledged CPU. It doesn't know how to do 4,000 different things. It only knows how to do one thing. With that in mind, if we go back to the monitor, could we create a virtual machine or even a piece of hardware? The monitors would have this built into them now. So that's kind of where we're going with this. But could we create something that's in charge of many pixels at once? A hardware circuit that's in charge of many pixels at once. Now, isn't a hardware circuit Is the CPU a hardware circuit? It's a collection of them, but yeah, it's a really complex hardware circuit, right? Could we have a very simple hardware circuit that's in charge of the brightness of 1 pixel? Could we have 500 of those hardware circuits, each in charge of 1 pixel, and then build another hardware circuit that's in charge of those 500? Seems reasonable, right? You know, if we start thinking about this in terms of electronics, it's amount of electricity is going to go into the guy who's in charge of 1 pixel, and he's going to adjust the brightness based on the magnitude of that electricity. Well, if we have the electricity go to this guy up here, who's in charge of the 500 guys, and then he can split it out, 500 ways to those things, we can then dim 500 pixels all at once, right? Because each of those guys is independently being controlled by a very simple circuit that only knows how to control brightness. Make sense? So now we've created parallelism. We've built ourselves space by saying we have a problem that needs to be solved that can be solved very simply. I don't need a processor that can do 5,000 things. I need a circuit that can do one thing. And now I can take that circuit that can do one thing, and I can duplicate it 500 times, or 1,000 times, or 10,000 times. And now we can call upon those 10,000 circuits to all do their thing all at the same time. So it's like massively multiprocessor, but we've replaced the processor with a simple circuit. Kind of make some sense? Is that a form of parallelism? That doesn't require scheduling? What does that form of parallelism require? So we use the example of it being like dimming a computer screen. In order for that to be worth it, in order for it to be fast, what does it require?
No communication.
Okay, or no logic. No logic at the simple machine level. We'll call them simple machines for right now. So a little tiny circuit that just decides how bright this particular pixel is, it's not asking any questions. It's reacting. Make sense? All right, so let's take a 10-minute break. We're going to come back and we're going to start talking about logic gates for a few minutes. And then we're going to circle back on the simple machine thing, and then we're going to talk about SIMD.